Guys, I did it. I finally got SOTA durian accuracy classification. So I have been trying to do this for a while, and finally I've received for these durians a very high accuracy of 99.6%. I finally reached very high accuracies, and this is better than the current state of the art durian classification. And so I am proud to say I am now king of durians. You may only refer to me as king now. And I am the only one that is able to differentiate between all the durians. Jokes aside, this is my second attempt at doing this. So I'll go through this process step by step to see how I change my code and change the existing work of the previous authors to improve their model and make it a lot faster and better. So let's start from the data itself. So the data that the current state of the art used is a very peculiar data set, because their images are very high quality. It's 8,000 by 6,000 or 4,000 by 300 in some cases. It's set here. And so it's very odd. Like, why would you need such high accuracies to just classify durians? And so I did some pre-processing. I scaled the images down to an average size of 800 by 600, 10 times smaller, and still good enough to classify. I'll show you why later. In fact, I'll show you now. In the code, we resized the things to 224 by 224. And if you're resizing something that's 8,000 by 6,000 in size to 224 by 224, not only does it take a long time, it's around 1 second per image, it also wastes all your space because you're just trying to get 224 by 224 worth of images. Thus, we pre-scale it down to 800 by 600 to increase our training speed and also to save some storage space. The original dataset is 20 gigabytes in size. This compressed one is only around 200 megabytes. So we load the data here, and following the paper, we only try to classify 3 types of durians, which is the black thorn, D24, and musang king variants of durians. As said here, we have about 1,000 trained samples, 273 validation samples, and 202 testing samples. So that's the data we are working with today. For the model, we are using a vision transformer. That is the latest model. In fact, I have things prepared. The vision transformer was released in 2020. Yeah, 2020. But the model the original paper was using is from 2016. And so we have 4 years of model advancements at our expense. And now we can use this much better model to try to classify durians. And that's what we're doing today. So you can see that our model here, this is the layout of the model. It starts with a convolution projection, yada yada. There's a lot of AI nonsense. But you can see that at the end, there's this thing called a head. And there's a linear layer which takes in 768 features and outputs 1,000 features. If you see the rest of it, there may be more 768. That's because 768 is the hidden size of this model. Or to say that inside the model, they are summarizing all the data into a vector of 768 units long array. And thus, when we try to get our output, we have to wrangle 3 values out since we're trying to predict 3 different values. So 768 array long, understanding by the model of what the durian is, and we finally need to classify it back to 3 classes, which is the 3 types of durians we want. However, this is 1,000 because the original model was trained for the ImageNet competition, which tries to classify an image into 1,000 categories. We only need 3, so in here we replace everything with a linear model from 768 to 3 features. So Here, there's another chunk of code I should explain. It's param dot requires grad equals to false. So for each parameter in the entire model, before we apply this head, we set requires grad to false, which means that we freeze the learning for that layer. Why is that so? Well, here we are adding a completely new and randomly initialized layer. And so the model might freak out. It's like getting a lobotomy. And so while freaking out, it might accidentally like throw a tantrum and destroy some of the learning it has done previously. Thus, we freeze this learning in place so that it is not able to disrupt that learning, and it has to learn to use this new classifier output layer before it can do the rest. And that's exactly what we do here. We learn for 10 epochs using this while freezing the rest of the model, and we go from 68% accuracy all the way up to, I think, 90% accuracy, which is pretty good already. So through this training, we slowly unfreeze the rest of the model. So now we set requires grad to true for the last layer of the encoder of the model, which means basically you don't need to know what an encoder is. You just need to see that this is the last model. We are unfreezing this layer since it's the last one. Later we are unfreezing this one, and then this one, and then so on. So yeah, here we are unfreezing layer 11, then later on it's 10, then it's 9, then it's 8, 7, 6, and then here we stop because we start flattening out. You see our accuracy is around 98% on validation. And so we pass it into the actual classifier for the test accuracy, and we get a test accuracy of 99.6%, which beats the state of the art of, I think, 92%, which means we are superior. And to show that this isn't a fluke, I downloaded some images from the internet and we classify it. So this is a black thorn, and it is able to show that it is indeed type 0, which is black thorn. We pass in this slightly more varied image, which includes the flesh, and it is still able to classify it as the correct one. In this case, it's type 1 or D24. However, when you pass something that's a lot more varied, you see there's a background color, there's a lot more different shapes, it is very uncertain. As you can see, the accuracies are all in the same magnitude, while for the rest they are like orders of magnitude off. This 80% accuracy, this has 99% confidence, but this one is around 50% max here. So that's why a reason is because for this model we didn't use any data augmentation at all. And so for part 2, which I'm still training, we are not only using augmentation, but we are training on all 10 classes that the dataset provides. As mentioned earlier, the current model only uses some parts, only 3 classes of the data. So now I'm still training the data to use all of the layers, as you can see. And so I'll update you on this final part of the project later on when I'm done. So yeah, in conclusion, we got to 99% accuracy just by upgrading the model and doing our own training quirks on it. Most of the upgrades are from the new model, since we didn't even use augmentation. So yeah, that's for today. We've done it. We've got the state of the art.